So today, the 2019 Nobel Prize in Physics was announced, being awarded to James Peebles, Michel Mayor, and Didier Queloz, honored for, quote, improving our understanding of evolution of the universe and Earth's place in the cosmos. So this is kind of a split prize between work done in cosmology, like inflationary cosmology, the expansion of the universe, and the detection of exoplanets. And so I wanted to walk you through what it looks like for us to detect exoplanets. So here's the picture we want to have in mind, is that there's some star out there in the night sky with a planet, this little blue dot going around it. And you can see the blue dot is really, really small. Like this is blown up. This is not to scale. None of the numbers in this program are to scale. I will leave that to you for homework if you would like. But stars in the sky don't even appear this big. The planets definitely don't appear this big, nor do they appear to go out this far. So this is kind of an exaggerated model here. But the idea is that there's a planet going around a star somewhere out there, and we want to be able to tell where these planets are, what are they doing, how massive are they, how far away are they from their sun, could they possibly hold water and therefore life as we know it. Now, normally when you think of a planet going around a star, you think of the kind of overhead view, right? Where you're looking like this, where the planet is going around in an ellipse. And usually we even have a little trail going around, but I've taken that off of this code. It turns out that's kind of difficult to spot. The easiest way to find a planet is when, let me hit refresh here. The easiest way to find an exoplanet, or a planet going around a star other than our sun, is where we are looking kind of parallel to the disk here. So we're not looking at it overhead going around like this. The easiest way to find exoplanets is where the planet is going around in an orbit that we are looking at as kind of like a flat line like this. So here, the exoplanet is coming around toward the star. And so what we are looking for is the effects of this exoplanet on the star. One of the effects we want to look for is when the planet ends up passing in front of the star, which it's about to do here in just a second. Because what we want to look at is the intensity of the light coming from that star. You can think of this as brightness. This is just written as a percentage of the star's normal brightness. But once the planet passes in front of the star, some of the light gets blocked. Now, it's a very teeny tiny amount, right? We're going from 100% to 98.7 something percent here. But there is a dip here, right? So whenever the planet passes in front of the star, we get a dip in the brightness because some of that light is getting reflected back toward the star, is getting scattered off of the planet so that it doesn't reach the Earth. So we get a little bit of a dip there every time the star passes in, every time the planet passes in front of the star. And so if we watch this over a long period of time, we can see multiple dips because every time that planet passes in front of the star, we'll get another dip. Here we've got the planet coming around for another pass, and so you can see in between these passes, the light intensity is pretty consistent. So this dip, even though small, is pretty easy to spot with a sensitive enough detector. And here it comes around again, coming around in front of the star. Again, it's going to block just under 2% of the light. So we get a little dip here, again, in the intensity after the planet has passed in front of the star. And so from this, we can get the period of the planet's rotation around the star. So we're going from just over 1 second to just over 4.5, maybe 4.6 seconds. So, or 4.5 units of time. All the units in this video are arbitrary. So from that, we can figure out the period. And once you've got the period, you can figure out things about the mass of the star. You can figure out the distance between the star and the planet. You can run simulations like this to get the parameters to match. The second way that we detect exoplanets is by looking at the wavelength of the light coming from the star. So this uses information about the intensity of the light. We can also look at the wavelength of the light. Wavelength, of course, tells you what color the star is or what color the light is that's shining through. Here, this is yellow coming in. So we would be looking at slight changes in the color of the star, or really in the wavelength is what we would measure. So that this one would have a slight shift in the wavelength, because as this planet is coming around the star is also wobbling just a little bit. Every star wobbles in response to every planet that orbits around it. Our sun wobbles noticeably due to Jupiter's orbit. So there could be aliens on this very exoplanet here looking at our star and figuring out that Jupiter is orbiting around it. They may or may not be able to tell whether Earth is orbiting around our sun. But if you come down here, I've got a graph of the fractional Doppler shift. So the change in the wavelength as a percentage of the sort of base wavelength of the star, the actual wavelength that it's emitting. And what you get here is a slight change. And again, this is very small. This is even smaller percent change than the shift in the intensity, but it is something that we can detect. And what you notice is that the period of the oscillations here is the same as the period over here. So this can kind of help us confirm that information, that whatever period we have on the light intensity graph needs to be the same period here. They're not necessarily synchronized, right? So a peak here doesn't correspond to a dip here, or a dip here correspond to a dip here, but it is the same period, meaning it's the same amount of time between troughs here and the same amount of time between peaks or between troughs here. And what this allows us to figure out is even more information, because now that we have the star's reaction to the planet, we can start to figure out the mass of the planet as well. Let me show you what I mean. So let's just take down a quick little note here that this thing has a peak. Excuse me. Let's just cut that, Brian. So let's just take down a note here that this thing has a peak of about 1.2 e negative 5 and a period of, let's just go from the lower part here to the lower part here. It's got a period of about 3.5. Again, the actual units don't matter. We just want to see what the change is. So let's go over to the code here. And let's change the mass of our planet. Let's suppose we make this planet, instead of a mass of 1 unit, let's make it a mass of 10 units. Let's make it 10 times as massive as it was before. Now we'll watch as our planet goes around the star. All right, here's our exoplanet coming around for its second pass in front of the star, now with 10 times the mass. Now what you'll notice is I did not change the size of the planet. I probably should have done that. So basically we've changed its density. That would change the dip in this a little bit. But you also notice that the period remains the same. Let's scroll down here. You notice again, yeah, the period, it's pretty much the same. It might have shifted a little bit, but I didn't have this level of accuracy on the last graph. What you notice about the peak is that the peak has increased by a factor of 10, right? So last time our peak was 1.2 times 10 to the minus 5. Now it's 1.2 times 10 to the minus 4. So the relative shift, or the shift in the wavelength, has increased by a factor of 10, just like it did with the mass. So by using all of this information, by using both of these graphs and all the information that's available, we can get lots of information about these exoplanets that are out there. So now that we've seen what it looks like to detect an exoplanet, let me just walk you through how this code works. First, we define a function that calculates the gravitational force between the planet and the star. I've used this several times, so I'll just include a link to the video where I first introduced it, so in case you want to learn a little bit more about how it works. Do note that we're using g equals 1 to keep our numbers of kind of normal size, so these are arbitrary units. If you wanted to make this into a real-world simulation, you'd have to change this to 6.67 times 10 to the minus 11, and then use real-world values for the planet and star mass and distances and everything. It's not going to show up terribly well in the animation, but it will get you the graphs correct. Here we create the star and the planet just using VPython's sphere function. The important thing is we have to give each of them a position vector, so location. We have to give each of them a mass, and we have to give each of them a velocity. And we do actually have to give them a radius. This radius is going to be important in a minute for getting that light intensity graph. And so in order to model the change in light intensity, this little chunk of code sets up a number of rays coming from the star. It is 50 squared, so that's 2,500 rays that are coming from the star to the camera where we're seeing it on the screen. So each of these rays starts at the star. So it starts at some point on the star and then moves out to the same point with the same x and y coordinates, but out toward where the camera is. So the camera is just the object that tells VPython where to render the view from. And so what we're doing is we're looping over a circle. That's what this little trick is with this square root star radius squared minus x squared. So this kind of double loop here will get you a circle going around the cross-sectional area of the star. So we've got 2,500 points of light coming from the star to the camera. And basically, we need to be able to tell whether the planet has come between the star and the camera along that light ray. And so here what we're doing is we're defining a function where we can tell whether the planet, the object here, is coming in between that ray, is intersecting with that ray. And basically we just check for a few inequalities here. We check for whether it's in between the, we check for whether the ray is in between the left edge of the planet and the right edge of the planet. We check for whether the ray is between the bottom edge of the planet and the top edge of the planet. And we check for whether the planet is in between the star and us. Then we move down here to our animation loop. This is just our standard Euler-Kromer update of updating velocity based on force and then updating position based on velocity. Again, I'll include a link in the description below to a video series that'll walk you through how we set that up. And then here we just check for whether for how many of the rays are being blocked by the planet. So we just loop over all of the rays in the rays list. And then we check for whether the planet has come in between us and the star along that ray. If it's not between us, then we count that as the number of rays that are passing through to us, and then we just graph that percentage of the total number of rays. And then down here we calculate the fractional change in the star's wavelength. This is just the Doppler effect equation to get you the fractional shift in the wavelength, and we just plot that again as a percentage. So this is pretty straightforward to use. You can play around with this to create your own star and exoplanet system. You could even create a binary star system if you wanted to. You just have to set up another set of rays coming through. But yeah, I think these graphs are pretty neat. They give you a pretty good idea of how we find these exoplanets. So I hope you enjoyed playing around with this code, and happy hunting.